Okay, so in this video I'm going to have a look at using Kruskal's algorithm to make a minimum spanning tree. I'm going to do two examples. So just remember as well that a tree is a connected graph that has no cycles, and a spanning tree then is a subgraph of a graph that includes every vertex and is also a tree. And what we want to do is make a minimum spanning tree. So we can see here we have a graph. It's a weighted graph, so each of the edges here have been given numbers. They could be, for example, distances between E and A and B and so on. A minimum spanning tree then is a tree of minimum total weight in a connected weighted graph. So a minimum spanning tree then is just a tree that we're going to make from, let's say, this graph here that is of minimum weight. Now they're also, by the way, called minimum connectors. So what we're going to do is use Kruskal's algorithm to make a minimum spanning tree for using this graph here. So let's start. Now what we're going to do first is just look at the edges, and what we're going to do is list the edges in order of weight. So let's take the edge first, write that down here, and the weight here. So we list all the edges and all the weights. So the first edge here that we're going to look at is AE here. It's going to be this one here. This is the smallest weight, so I'm just going to write that down here. AE, and it has weight 3. The next one is AC. That has weight 5. Now I could also go with EC, so you can go with either one. So I'm going to go with AC, and that has weight of 5. So I have two edges now. So what I might do is just draw the minimum spanning tree, or at least start drawing the minimum spanning tree. We have AE and AC. So let's draw it down here. AE, which is here. So we have A here, we have E here, and we know that that has a weight of 3. The second one was AC, so that comes down along here. So let's draw that. So that's going to be down this way. Let's just draw it on a little bit more. So this is a C here, and this has weight of 5. Okay, so there are our first two edges in our minimum spanning tree. So let's keep going then. So we have AC and AE. So the next one then is going to be EC, which is also 5. Now if we look at EC here, if we joined up E to C, we would end up with a cycle here. Now remember, a tree has no cycle, so we ignore that particular one. I'll write it in here, but we're not going to use it on this occasion. So let's see, this is EC, and it has a weight of 5. We're not going to use that one. Okay, the next one is BC. BC is coming up along here, and that has a weight of 6. So let's write down BC, that has a weight of 6, and that one I am going to draw. This is B here, and that has a weight of 6. Okay, so still we have no cycles. Let's keep going then. The next one then is BE. So let's have a look at BE. So BE comes over this way, and you can see here that if I did connect B to E here, I would end up with a cycle as well. I would connect from here to here, so I would end up with a cycle. So I'm not going to use that one. That has a weight of 7, so I'm not going to use that one. The next one is AB. So AB will also create a cycle. You can see if I join A to B here, we'll end up with a cycle here. So I'm not going to use that one either. I'll list it here. That's 7 as well. And the next one is ED. So ED has a weight, we can see here, of 8. Now that will not cause a cycle, so I'm going to use that. So that has a weight of 8. So let's just draw that in here. So I'm going to go from here down to here. This is D, and it has a weight of 8. Now we have all the vertices at this stage, so effectively we're finished. But let's just finish off the other ones anyway, just to show you that we will end up with a cycle if we had used the other ones. So the next one is BD, which has a weight of 9. We're not going to use that one. BD will give us this line here, and that will create a cycle as well from here down to here. Next one is AD. So AD then, that is also 9. Again, we're not going to use that one. That will also cause a cycle. So from A to D, then from here down to here, that will cause a cycle. And finally then we've got CD. CD goes from here to here, and that has a weight of 10. Again, that's going to cause a cycle. You can see here, if we connect these up, we'll end up with a cycle here. That has a weight of 10, so we're not going to use that one. So that's it. This is our minimum spanning tree for this graph here. You can see that it is a tree. It contains all the vertices, and there are no cycles. So what's our minimum weight then? So all we got to do is add up all these numbers here. Our total weight then is just going to be 8 plus 3 plus 5 plus 6, which will give us 22. Okay, so that's our minimum weight here in our minimum spanning tree. Now what you will find, if we'd have used, let's say, this one here, EC, instead of AC, they're both the same weights, we would end up with a different looking spanning tree, but we'd have ended up with the same total minimum weight, and that would in fact end up looking something like this. So we would have A here and E here. That had a weight of 3. So remember, instead of using AC, we're going to use EC. So we're going to come over here. So C was over here. Remember, that had a weight of 5. We still would have used this one here up to B, which is 6. And we'd have used this one here as well down to D, and that had a weight of 8. You can see here that we still would have ended up with a total minimum weight of 22. Okay, so that's the first example. We're going to do this example here now. This one here is a table of values, so it could represent, again, distances. So what we're going to do here is look for the minimum distances again, list them and draw our graph. Again, we'll do a table, so we'll call it an edge and a weight. Okay, so we can see here that our smallest edge here is actually 58. So I'm going to start with that, and that's from A to C. So let's write that in here. So from A to C is 58 kilometers, millimeters, whatever it may be. So that's from C to A. So let's start drawing this as we go along. So it's from C to A. So let's take C here and A here. And that has a distance, let's say, or a weight anyway, of 58. So that's our first edge. Okay, let's have a look at the next one then. The next one is actually going to be 62. So let's just cross those out. 62 here and here, and that's from C to D. So from C to D is 62. So let's draw that one. C to D, 62. I'm going to draw it down here just in case I needed to connect it to something down here as well. CD. So that's that has a weight of 62. Okay, next one then is actually 72, I think it is. So 72 is here. Should be another one here. So 72, and that's from A to E. From A to E. That's 72. So let's draw that one. So from A to E, let's draw that down here. And that has a weight then of 72. Okay, so the next one is 79, and that's from A to B. So you can see that here. So let's just write that in. So we've got A to B, and that has a weight of 79. Let's draw that in. So we have A to B with a weight of 79. Okay, so almost there now. So the next one then we're going to look at is from B to F, which is 98, has a weight of 98 here and here. So B to F, and that has a weight of 98. Let's just draw that in. B to F, the weight of 98. Okay, we've actually used all of them at this stage, so effectively we're finished. We have A, B, C, D, E and F. We have all the vertices in there, so we're finished at this stage. Now again, if we just add up the totals here, the total minimum weight again is just add up all of these and you get 369. This is the weight of our minimum spanning tree for this particular graph here, this particular table here. And that's really it for Kruskal's algorithm. By the way, I should mention as well that Kruskal's algorithm is what's called a greedy algorithm. In other words, it uses the next minimum value in the graph without thinking of what's coming ahead in the future. So it just kind of eats up, if you like, the next weight, the next minimum weight that it comes across.